I'm a particle physicist, as some of you may know, and I just wanted to talk about something that's basically is some thoughts rather than published work and so on and so forth. Just to invite the public, the quantum scientists and the relativists for discussion on this. And so the broader topic would be is how we can use quantum sensors or quantum technologies as a particle physics detectors. So since I'm a particle physicist, let me first set up my language, or at least as close as possible to others, so we understand what we are talking about. And so the prime model, or the theoretical model, actually theory, which we work with in particle physics, the standard model. As you know, this is empirically extremely successful, what you could call the fundamental description of strong, weakened electromagnetic interactions. And behind of this experimental success, there is an even more amazing theoretical framework. And this is based on relativistic local quantum field theory, and the interactions are described through the gauge and varying. So many times in previous talks on gravity, that the gauge and varying is quite important, as we understand, for the description of fundamental forces. Now, so the theory is very successful, but we also know quite well that the theory is incomplete, and there are various arguments you can hear from various people on that. One is the theoretical arguments about the construction of quantum field theory, and another is, and in particular, how we incorporate fully quantum gravity in this picture. And of course, there are observational, of course, evidence that the theory doesn't describe everything we observe. In particular, dark matter, for example, if you think about it as the ordinary matter, is not in the standard model. Okay. Now, let me motivate what I want to, the key message here, and start with the key things about the quantum field theory. So, I apologize to the expert. This is pretty, simple stuff here. So, we based our observation of so-called local observables. So, this the operator value fields and the product of those, and the various expectation values of these operators entering into physical observables like Hamiltonian and so on and so forth. But when you start considering already at that level, the product, local product of fields, you know that it's not defined, it's singular. And you can see this by reluctant non-locality, introducing some non-locality. Of course, this is a generic statement about this thing, but you can very easily evaluate that for the free fields, and you can see that this product, when you say a local limit, is divergent, and you could make sense of it. And of course, we can make sense of it with a judicious subtraction of these infinities from the physical observable that we call the cross-jet renormalization. You can do this not for all theories. For example, if you take gravity and you do the same thing in theory, in set of limits, for example, quantization, everything goes well, but you need to do the renormalization of infinite number of parameters in your theory, which means the theory is not predicted at all. It's not a theory at all. Okay, so then you can ask the question, why I just consider non-local theories. Okay, so based on non-local products of operators like this, and you can do that, and we have very successful of that kind of theory, which is not a kind of field theory, but it's a kind of string theory, which carries this basic non-locality in it. But Not always, but in most cases of the discussion, you can represent these non-local operators with local operators and extra degrees of freedom added up. Okay, so that's how we think about the particle physics. Okay, so there is a theory of until certain valid certain scales, and if I want to consider beyond of the scales, I have to introduce a new degree of freedom. So that's the usual thinking about. And that's how the particle physics experimentalists think about the theory. The message is you have to resolve these apparent non-localities by depositing enough energy in a very short period of time to disturb the vacuum and produce the particles of mass m, for example. Okay, so that's what experimentalists expect. And so that's what basic thing which Rutherford told us in earlier last century, and with, the experiment is continuing the same way for centuries now with Large Hadron Collider, Bell-2, and other experiments, collider experiments. Now, so another thing to notice that although this is a blend of quantum and relativity together, this type of experiments, but when it comes to the particular observations, it's all the measurements are of classical quantities like energy deposited, for example, calorimetry, or particle tracks to measure trajectories and so on and so forth, just to identify what was born in your collision. So this process in LHC, for example, you can estimate what are the scales we are testing the theory, these ideas of relativity, and this is quite astonishing. So we're testing at other scales. Essentially, if you think about the quantum mechanics and relativity, at least in those forces we know. Now, I usually don't talk about money, and I don't want to talk about money because that's not the issue, what I understand. But the main issue, of course, is the technological one. So, for example, if I want to go this way and test the theories of quantum gravity, I have to resolve the distances close to the Planck scale, where the quantum gravitational effect becomes important, and where I would expect to have some particle-like states produced, maybe. And to probe this type of distance scales, I have to build up with the current technology. I have to build up a collider of the size of 10 to 10 meters. And to put it in perspective, this is 1/10 of the distance from the Earth to the Sun. Okay, so that's presumably the more major problem than the matter itself. And this is what I motivate not only myself, but there are now a growing community of people in particle physics and also on quantum side who think that maybe this growing and developing quantum technologies may be the way out, or at least for certain phenomena to be tested in a very different way. So, for example, if we measure the observables which are not directly related with local interactions, so then means that, and I can extract a certain information about the physics at the local scales. So that could be a way of doing experiments in quantum physics. In particular, measuring, for example, interference effects, or entanglement, which are induced by the local interactions. So, another thing about thinking about a different type of experiments is the following. So, suppose I have already particles as the cosmic relics in the universe, and they usually very rarely interact with the matter, and usually deposit very low momenta. So the momenta exchange is very small, which normal detectors cannot detect. But quantum control and manipulation can be considered actually very sensitive impulse detectors. So there are these two main things which you can think about using quantum technologies as a particle detectors. Okay, so as I said, I don't have any very particular proposals here, but I'll show some. But to illustrate the thing, let me illustrate on the way how, for example, the famous Aron-Bohm effect works. So here we have a typical setup of the solenoid. It's infinitely long. I don't care about the effects on the boundaries of the solenoid and of the size of A. And you know that when the electron circles around the solenoid, it picks the Aron-Bohm phase. And Aron-Bohm phase is essentially defined by the vector potential in electromagnetism, which couples directly to the current of moving the electron. And you can obtain the result, very famous result, that the phase depends on proportional to the flux of the magnetic field through the solenoid. And this is kind of this effect, of course, can be measured then in the interference as an interference effect. And we know that this is not related to any local interaction. So obviously, because on the way of the electron essentially propagates in the vacuum where the magnetic field and the resulting forces are zero. And now there is one tricky thing here. That's why the gauge invariance comes in a specific way. You may say that if Lorentz force outside of solenoid is zero and it's vacuum, and there is a gauge invariance, they can describe equivalent with the physics with another gauge potential, and so the observables should be the same, which are related with my gauge potential, which includes the phase by this relation. I can choose this constant arbitrarily such that I can nullify the potential, and you may think that, okay, so the effect disappears. And of course we know this is not the case, and it really depends on the topology of the problem. The topology obstructs taking this gauge. Okay, so the effect is real. So there are two things attached to this. Just is the gauge invariance and the topology of the space which are made of the electron moving around the solenoid. Now let us imagine now that the electron we considered in the previous case carries other charges. So it carries other charges, say lepton charge, which also has a carrier of in terms of some vector boson x mu. But in this case, the vector boson is massive. Okay, let me consider this case. Of course, if you want to compute now the static potential, which is induced by the interactions which are mediated by this gauge boson, then instead of Coulomb potential, you now have this Yukawa type of potential, which is short range. And of course, this means that at large distances, these interactions are not observable. Right? So we say that the charge, new charge, which I attributed to electron, is screened at large distances. And here, if I want to measure the charge, I have to go and resolve the distances, which is of the order of inverse quantum weight of the boson which mediated force. Now, however, if I insist on the gauge invariance, and we know that the gauge invariance must be for the description of spin particles, then the mass of this field has to appear through the so-called Higgs mechanism. And in the Higgs mechanism, I have two terms. Here, the mass term, which is written this way, and the term which interacts with the current of the electron with the vector field, or Lorentz invariant way. Now, of course, in the fully gauge invariant theory, these combinations are completely equivalent. However, if there is an obstruction to the gauge invariant, then that two interactions won't be equivalent, and therefore gauge equivalent, and therefore you would expect to have, even in this kind of theory where the local charges are hidden and screened, you would expect to have Aron-Bohm phase. If that phase is measured in terms of a usual Aron-Bohm phase, has a less, it's smaller, suppressed by the 1 over mx, the mass of the photon. But nevertheless, if we can, if there is no exponential suppression anymore in the phases, and therefore if we can measure interference accurately enough, we can infer the existence of short-scale physics. And so next, I wanted to now go on another path and to talk about trapped ions as particle detectors. Now, that's not an original idea. There were recently a few papers appeared when the people were discussing, for example, newly charged particles, detection of so-called newly charged particles or trapped ions. But what I want to discuss is a particular discussion of the magnetic monopoles, the detection of magnetic monopoles with the newly charged particles. Once again, the idea is the following. The key message is the following. So, suppose we have a trapped ion, which the motion of it which can be very well controlled, and the quantum state is cooled down to nearly ground state. And then, suppose there is an extra particle which interacts with our trapped ion and transfers the momentum, say delta p, and you can then, if delta p, of course, is given by this relation, obviously it's a classical energy, so the ion gets excited, and the excitation is larger than omega, then you can detect those excited states. Now, if you estimate the minimum momentum which comes out of these simple relations, this is standard quantum limit relation for the momenta, and this is on the particle side, is very, very low momentum transfer. Okay, so the trapped ions can be at that simple level sensitive to very low momentum transfer. So that's the basic idea, and the rest of the talk. I just want to give you a back-end level of estimation of the sensitivity for the magnetic monopoles. Now, the magnetic monopoles, the story was introduced by Paul Dirac back in 1931, and since then they are all the time around, especially in fundamental physics, to the point that people realize something which is known as a completeness conjecture. That if we observe in nature the quantized electric charges, the complete state, completeness of the state requires the existence of magnetic charges as well. Okay, so this is the idea which goes back to Polchinski, and in most of the theories we know this is indeed true. And the reason for that is, of course, is that the electromagnetic gauge group with the quantized charges becomes compact, and the compactness of this usually means that there are monopoles as a solution in the group. Yeah. Okay. Yes, and we have a lot of examples of this explicit solutions of the monopoles, like in ground unified theories, etc., in string theory, etc. Now, of course, we had no observation of fundamental monopoles so far, except of this Valentine Day discovery, very famous by Blas Cabrera, the only claimed discovery of the monopole. But as you know, since 2019, there was a lot of progress in condensed matter physics to show that monopole quasi-particles exist. In this explicit demonstration for this. A few properties about the magnetic monopoles. We don't know many. It's model dependent, but generically you can think about the magnetic monopoles having a very broad range of masses from a TeV scale. Now this is constrained from the LHC experiments up until the Planck scale, for example. That's what I would call the traditional magnetic monopole. If the masses are larger than 10 to 19, that's also possible. Then presumably they are realized as magnetically charged black holes. Okay, so discussed this already, some of those solutions, but this is believed to be true. Okay. Now, obviously, if this is that massive, and this is the indication coming from, they are hopeless to produce it. Okay. So we need to, to think about some other ways of. Now, on the other hand, this is a magnetic monopole's lowest mass in the spectrum. They are stable particles because of the conservation of magnetic charge. Electron, the lowest charged particles, are stable, and therefore, if they were producing them in the universe, and there are magnets to produce them, they will be here around as a possible element. Okay, so that's believed as well. Now, another very important thing about the properties is the fact that, which is very interesting now, on the quantum consistency of the existence of monopoles requires the quantization of charge. Okay, so that's where the conjecture comes from. In fact, and if you write down so all the interactions of this monopole, of course, goes through the analog of the fine structure constant, or the magnetic fine structure constant, and of course that's huge, okay? Because it's inversely proportional to the electric fine structure constant. Now, if we have a black holes similar, so what happens is the stability of the black holes is only in the extremal case. Okay? The extremal black hole, magnetic black holes, are unstable, and so the magnetic black holes are related to the mass of the black holes, black mass to the square. Okay, so in any case, the interaction strength, which is produced, or the potential of magnetic potential, which is produced by these objects, are huge compared to the electric potential. And you can look at the force between the ion and the monopole as the usual Coulombic force, because the exchange is due to the photon. It's a long-range force. And you can compare that the strength is really huge compared to the usual interaction of electrical charge particles. Now, there are, of course, a lot of searches before of these magnetic monopoles, and there are bounds on the fluxes in today's universe and in the galaxies. One of the most robust bound comes from the fact that the monopoles moving in the galaxy, they're accelerated by the galactic magnetic fields, and they get the kinetic energy from them, and they deplete the magnetic field. So, but the existence of magnetic field will depend on the flux abundance of this monopole. So these are so-called very famous pocket bounds. Then, of course, you shouldn't overproduce those monopoles in the universe, and we have a bounce from the mass density of this monopole should be less than the matter density, the usual matter density. Okay, so these are the bounds, and if you know the bounds from the flux, then you can ask the question, very simple, back and analog calculation again, how many of those monopoles wandering in our galaxy can reach us on Earth, and this calculation is again very straightforward. So these are the typical number densities in the various cases. So here I parameterize the deviation from the Parker bound as this kappa. Okay. Now we are talking about what would be the cross section of the monopole passing our trapped ion system. And again, if you look at the geometric cross section in this case, pretty safe, it's a classical object, and you can do the estimation and find out that the effective cross section is given by this formula, which is quite large. It's mainly because of the largeness of the effective interaction between monopoles, and also the fact that they are not very heavy, they are very slow in the visualizing environment. And then you can compute the rate of how much they can interact with our ions, and these are the particular rates estimation that this. So this naive or very envelope calculation tells you that you can have an improvement over the current by or so, which is quite substantial. But of course, this is a very preliminary background envelope calculation. So let me conclude now with this. So I believe that the quantum technologies provide with new and in many cases unique opportunities to test the fundamental physics. And there are a lot of other areas where you can do this things. The measurement of non-local observations, interference and entanglement is a very important thing. You can extract information which is otherwise unavailable for local interactions, and they're sensitive to rare events through the low recoil measurements, like the monopoles. It could be some type of carbon. So, thank you very much.